Okay, we can. We, I was going to do homework problems. Yes, forgot about that. Now. Um, we're going to finish this up, and then I am going to add like 2 more videos with the capacitors and showing you 1 or 2 of the capacitor homework problems. So you got 2 videos after this one, but those are definitely for Monday. Okay. All right. So here we go. Let's take a look at this problem here. So this one, yeah, this one causes a lot of heartache for folks. It says find the total potential at point P. All you do is put in the chart, and D is equal to 0.47. All you have to do, you don't have to do any kind of vector stuff. That's the beauty of this, is that this guy is this KQ over R, negative KQ over R. This guy's negative KQ. Now, let's take a good hard look at this. Let's take a good hard look at this. If this guy is positive KQ over R, and this guy is negative KQ over R, what happens? Well, he's going to have a potential here. This guy's it's going to go to 0. So it's basically going to boil down to the KQ over R between these 2 guys. And this is KQ over 2R. Well, let's just look at what happens. Okay, just conceptually, I'm just going to do it all. I'm not putting in any numbers. You all can do that later, right? So let's just look at. I think this is what we have. Let's just draw it simpler. Q. Oh, I got to make sure that I got the positive, negative, positive, negative, negative. Okay. Positive Q. Here's point P. Negative Q. And a negative Q. All right? And these are all a distance D apart. Add them up, Buttercup. That's all you have to do. Take it one piece at a time. So you're going to do minus, well, let's just do it K minus Q over D plus minus K, or let's do it K minus Q over D, okay, plus KQ over D plus KQ over 2D. First of all, what can I factor out of everything? You got it, KQ. And so I've got minus 1 over D plus minus 1 over D plus 1 over D plus 1 over 2D. Ain't that hard, people? All right, let's go. Let's look at another one. But you needed to see what was going on. Okay, you needed to see it, I think. Voltages are nice. We just add those puppies up. Now, this is what we like to do. We like to bring 4 identical charges are brought from infinity and fixed to a straight line. Each is 0.55 from the next. Determine the electric potential of this whole group. So we've got to find the electric potential, the voltage of this entire group. And we're doing this exact same thing we just did. But we're going to have to be careful and do it one at a time. Okay? We're going to have to be careful and do it one at a time. And then it's really kind of fun. It's kind of nice. You're just building, it's like Legos. This is a Lego problem. All right? This one was 17. Gosh dang, I just flipped my pen around. This one is 17. And then now let's look at 26. And again, I'm not going to do anything fancy. I'm not going to do anything fancy. I'm just going to write it out. Okay, so each of them are going to be on a straight line. They're all the same charge. They're all a positive charge. All on the same line. So you just start off. You just go, okay, positive Q. Cool. Now, this positive Q, this first Q1, which is still the same, this is V1 out here. This is being caused by V1. Are we going to need the electric, excuse me, the electric potential energy or the electric potential? Okay, determine the electric potential energy of this group. This is way cool. I had to read the problem again. So right here, so what's happening here? Let's draw a bigger picture. Here's that positive Q. And then out here at that distance is a hole. Okay? Is a hole that we're going to put a charge in. Okay, when I bring this charge out from infinity, here's my infinity pile. And then when I bring this charge out here and plop it in here, well, first of all, Q has caused a voltage to occur there, right? So you got KQ1, they all happen to be the same, over R is equal to V1. So the energy when we brought charge 2 in, the electric potential energy that when with 1 and 2 is equal to Q2 times V1. Okay, and we'll just keep going. All right, so now now we're going to bring another one out from infinity and put it here. All right, that ain't hard. No big, but we got to be careful because now I've got V1 in position 3, which is going to be V1 in position 3 is going to equal KQ1 over 2R. But wait, there's more. Plus V2. So this guy's causing the potential and this guy's causing the potential. Plus I've got V2, which is KQ1 over R. It's causing that one. So at this point, when I bring this guy in, the energy is going to be electric potential energy when I bring in all of 1, 2, and 3 is going to equal the electric potential energy of 1 and 2 plus the electric potential energy of 3, 1, 2, and, well, don't want to do that one. The electric potential of 1, 2, and 3, that's going to equal Q3 times V13 in position 3 plus V2 in position 3. And then you're going to calculate that, and then you're going to have that one. Then you'll do it again for the fourth charge, which is going to be out here. All right? Kind of tricky, but not bad. So let's look at one more, and then we'll, that'll get you started. And then this one's probably the trickiest one. Those were kind of building the, how much energy did it take to build that thing? Okay? Because remember what we're talking about here. Since this is a positive, oh, let me show you. Since this is a, were you watching that the whole time? I just realized something. You may not have been watching that the whole time. Hope you were. I'll have to go back and see. If not, I got to redo this. All right. But anyway, here's the deal. Here's what I was talking about. Now I've lost my train of thought. Oh, here's what I'm talking about. See, we got this charge Q. When we bring this guy in, it's a positive charge. It does not want to come here. So I'm raising the electric potential. I've got to use an outside force. Some kind of outside force is bringing that charge up next to that positive charge because it does not want to go there. So it's just like when I'm picking up something up off the ground. I got to apply a force to work against gravity. I've got to apply a force to work against the electric field here. So therefore, I'm raising the electric potential energy of the thing. That's what we're looking at. All right? So let's look at one more problem. This one. Okay, a spark plug. Oh, this is just like what we did. That was the last problem. What's the one where they, so we can do that one maybe in class. Here we go. This is one that's kind of different. This is problem 32. Okay, here's problem 32. Now, an equal potential surrounds a point charge. Aha, I brought a visual. Okay, so inside this guy, the electric potential is all the way around, and it's the same all the way around the outside of him. I just can't draw it very well. Okay, but now notice, so it's the surface area of that sphere, of that styrofoam ball that I showed you. The surface area is 2.3 meters squared. So let's just draw what we have on the inside here, and I'll show you what I'm talking about. This is three-dimensional, man. So we've got this. I'm going to try and draw a three-dimensional thing neatly. Okay, I've got this positive charge sitting inside here. Okay, so that means back here, all over this surface, is a certain voltage, because it goes this way, comes up here, goes over here, comes back this way. These are all R's, by the way. Okay, those are all the distance R. Okay, and they're all the way around. So that's a surface area. And the voltage is equal to KQ over R. How do I find R? Surface area of a sphere, 4 pi R squared. They gave you this number. You've got to tease the R out of there. Then you've got it.